So it's a real pleasure to welcome Nathan back to the JQI. Nathan has a long history of BEC research and a long relationship with NASA's Jet Propulsion Lab going back to his PhD work at Caltech and JPL. He got his PhD in 2006 studying all optical spinor BECs. And I've known him for nearly 15 years. So Nathan, I don't know if you have contemplated that it's been 15 years almost since you came to the laser cooling and trapping group, but it has been that long. He was an NRC postdoc and he studied cold atoms and optical lattices and did a lot of work doing magic wavelength or magic conditions for trapping cold atoms in an optical lattice for quantum information applications. He's been, since 2009, he's been a professor at Bates College, and in 2014, he reestablished his relationship with JPL as part of NASA's Cold Atom Lab in Space project. And today he'll be talking about producing and studying BECs in a shell configuration made possible by the microgravity in the CAL experiment. So Nathan, take it away.
Thank you, Trey. It's really a pleasure to be speaking to a JQI audience again. I was here, I think 4 years ago for a sabbatical, which was immensely restorative and fantastic. And I'm excited to tell you guys, you folks, all about what my collaborations have been working on recently. So just to get right into it, if you look at the upper left on the screen right here, you'll see silhouette of the space station. On the upper right is something we've been able to make on the space station that I want to tell you about today. So there we are. So thinking about it, this kind of bigger picture, starting out, looking at the last, kind of now generation of BEC work, when we look at the physics of ultracold gases, we really look at what can happen in our labs. It's made consequential by temperature, geometry, dimensionality, topology, interactions. As we vary these things, as we play with these handles in our lab, what do we see in terms of many body physics, in terms of single particle physics, and just in general, the physics of ultracold gases? And over the last 20, 25 years, we've been able to, in the community, vary these quantities and explore this parameter space to varying degree. And I think what I want to talk about today is, one particular case of, how we can envision new places, physical, new laboratories for quantum systems, but also just new trap environments, new geometries, topologies for quantum systems that allow us to ask new and interesting questions. So today, I'm kind of right in the middle of a motivation part of this, but I want to tell you a little bit about the NASA Cold Atom Lab that's aboard the space station right now. Spend some time telling you about the shell structures, the shell-like structures we've been able to make with ultracold atoms aboard ISS through remote operation, and kind of run through the first science run observations, at least for my slice of the Cold Atom Lab investigation time. And I think I'm used to giving JQI sort of being at these seminars, so feel free to interrupt and query me as to anything that's unclear that you're curious about as we go along. So these are some new graphics we've gotten a hold of that I think are a little bit more illustrative of what we're trying to do on the right there. So what we're trying to do is to look toward making a shell or a bubble geometry BEC, or to look at the physics of ultracold gases confined to the surface of a sphere, or more practically, an ellipsoid. So I think there's I might as well be a little honest in here, and part of this is like looking at the last 20 years of history, and anytime we look at a new geometry, new dimensionality, add new handles to these experiments, interesting things tend to happen. And that's not a justification for exploring a route, but I'd be lying to say that it doesn't float in the back of my mind as to how this came about. It's something interesting that was new and a new geometry that hadn't been available before. But if you think about the physics open questions, I think it's not clear, and it's not clear to me certainly, how vortices behave, sorry, on curved surfaces. I think it's an open question how the thick shell to thin shell crossover could work. So if you look on the right side there, we start off with a BEC, a little gray blob there. if we were to inflate this into a shell structure or a bubble structure, you can envision having a thick shell as follows there. Or you can envision having a thin shell where the little red lines there illustrate a sort of relative thickness or thinness of the shell. These cartoons are really intended to illustrate where atoms would live in such a structure, but the trapping potential, the temperature, the atom number, the strength of interactions all would dictate the specific density distribution of any structure that you would construct like this. The third bullet there under open questions that we're interested in is kind of cryptic, but it came out of some questions I got at one of these seminars a few years ago. It's really, as you inflate these and you make these shells larger and larger, what does it mean to get into an ultra dilute limit? If we get to the limit of the densities, even probably 2D densities dropping really precipitously as you get to sort of millimeter shell sizes, how do we understand adiabaticity? How do we understand phase uniformity across these structures? How do we understand the nature of BEC when it's that large and that kind of strange of a geometry? In terms of more the physics playground area, we could think of doing things dynamically with shell structures like this, inflating them, much like people have done terrestrially, like in Gretchen's lab here, with ring-shaped condensates. Looking at the collective modes of condensates in these geometries, so looking at how a shell could oscillate like in an accordion, sort of a spherical accordion, or in more complicated, even azimuthal modes. I think a lot of theory thought so far in the literature, and there's not admittedly a ton, has been looking at what happens when you release these. How do these shell structures interfere with themselves when you release them? And can the interference patterns you get from a shell BEC interfering with itself tell you anything about what was going on in that condensate?
Nathan, it's Charles here.
Charles.
Do you know if you have a thin shell in a like you show there, but it's very thin, approaching sort of a 2D, is there a Kosterlitz-Thouless transition, or does the spherical geometry affect that?
I don't know for sure, Charles, and I think this is one of the areas where there's just been a kind of initial probings of theory in this. There's definitely a kind of a well-defined notion of becoming 2D there, but the behavior of vortices in a curved geometry like this with kind of different boundary conditions, I suspect complicate things, but I don't have a pithy answer for you on that. And this is essentially why that question mark is there besides BK, right beside BKT, in that whenever I mention 3D, 2D crossover, everyone asks about BKT physics there, and rather than just waving it away, I want to acknowledge that it is an interesting place to be thinking there, but I don't actually have a prediction of what should happen there. Along the way, there's some sort of more interest to the people who actually build these experiments, engineering aspects of this, so understanding more about the RF dressing physics that we use to make these, understanding how temperature in these shells is affected by the expansion and how you can get colder and colder and colder by expanding these and what that means. But I don't really put that at that level of kind of the open questions or the physics motivation. So this idea has been around for quite a while, and if you dig around in the literature, Barry Garraway at Sussex and Zobe had the first real explication of this idea in a PRL in 2001. If you look a little harder, there's a conference proceedings in the Acta Physica Slovakia from the year before that I like to cite, just because it came before. But I actually like to cite it because the title is a little more evocative of what we're doing here and looking at the properties of coherent matter wave bubbles. So it's an old story and an old idea to do this, but it's been difficult to do in the presence of gravity. And the reason is just gravitational sag. So if you actually try to make one of these ultra-cold bubble systems terrestrially in any kind of practical manner, gravity, or just potential energy from gravity, will sag everything down to the bottom of the shell. So you actually end up is not a giant ellipsoid of cold atoms, but more of like a contact lens ensemble, a little dish. And this can be a feature. This is, there's a path to making disk-like 2D condensates. And Helene Perrin's group in France has done this. But it's a real gravity means gravity is a real limitation for doing anything practical with shells here. So most experimenters in this area are used to trying to operate without gravitational constraints. So you could try to magnetically levitate. You could put on a gradient in most of our labs and levitate a single spin state. And the trouble is that the tricks we have to make these shell structures involve multiple spin states of different signed magnetic moments. So magnetic levitation really isn't going to work. It has been proposed to use electric or Stark shift levitation for this, and it's been theoretically doable, and it's not impossible, but it's very, very tricky. You need a lot of laser power, crazy requirements on uniformity, stability requirements. Garraway actually proposed this in the original PRL from 20 years ago, but kind of dismissed it as difficult right away, but it hasn't actually gotten significantly easier. There's a group in Tokyo that has made some progress doing this on kind of tens of micron length scales for canceling gravity, but it's not at the scale that would be necessarily applicable for bubbles yet. Another way you could do this is actually just make your condensate machine and drop it, lift it up to the top of a tower and drop it. And some German groups have used this drop tower in Bremen to do this, where they hoist a condensate machine about 100 meters up in an evacuated tube, drop it, do some BEC physics, catch it in styrofoam peanuts at the bottom, and do that a few times a day. So it works, but it's very low bandwidth and pretty difficult. You can also take your condensate machine and put it in an airplane and fly it up in the air and do ballistic launch and coasting, and probably get a few, I think they get, of order minutes that way. Or you can also do this in the lab and just build an apparatus that throws up a BEC machine, catches it, on a kind of 10-second or few second time scale. So this problem is solvable terrestrially, but it's tricky. You could also just put everything in a rocket, as the same German groups have done. And I think the first one launched a couple of years ago, where they put a BEC machine in a sounding rocket, which is a phrase that I hadn't learned until then. Shoot the rocket up, it goes into ballistic flight. You get 6 minutes of microgravity, and then a parachute opens, and then you go recover your machine if you can. This was launched in, yeah.
This is Bill. I noticed that on your previous slide, when you were talking about the vomit comet, that you'd crossed it out. I was wondering whether that term had become politically incorrect now. But
I was trying to maintain a semblance of decorum.
Actually, I did have a serious question though. Is one of these airplane solutions, which gives you, I don't know what, 20, 30 seconds at best, is it good enough? That is, my understanding is that you get to maybe 10⁻²g, which isn't anywhere close to what you get in the space station. I mean, and I think maybe you'll talk about the fact you don't get to micro-g in the space station either, but it's a whole lot better than what you get in an airplane. And so I'm wondering, is the airplane good enough?
I think the short answer is I would have thought maybe 5 years ago, but now I don't think so, because I think you'll see in some of the later slides, I show what happens if we apply like milli-g type accelerations to our system, and it's bad.
Okay.
But I don't actually worry about the kind of tens of micro-g that we end up with on the space station. I don't think I talked too much about that, but I can come back to it if you want later.
Okay, thanks.
So if I could follow on that, there's this magnificent drop tower near Bremen, where these prototype experiments are done. Are there transients in things like that, or do they give you as good a free fall as you would see in the ISS?
I think it's pretty good. I don't think the ISS necessarily offers better pure value of the microgravity than the drop tower. Probably when you start looking at, I don't know, it's kind of when you're getting down to the micro G level. I don't know what the Bremen spec is, though. I suspect it's in the tens of micro G, but I'm not sure. The problem with the ISS, and this is sort of maybe arguing against it, is that there's a jitter, right? Because you're sort of shaking a little bit, and then every I don't know, a few months or so, you've got to have a heavy DC acceleration to boost your orbit back up, and depending on what you're doing, that might mess things up. So one concern that I haven't really talked much about, but I think is a big deal, is that it's kind of bandwidth of doing experiments. So if you actually want to do more than a couple shots a day, or just have 1 6-minute period of making condensates in, in a year or so, like with a sounding rocket, you want to be able to put your BEC machine in perpetual free fall. So you could do that in a couple ways. You could put it in what the NASA people call a free flyer, just a satellite of some sort, or you could use the space station. So this is kind of a long story behind how this got created, which I'm not really going to go into, but the short answer is if we want to do free fall BEC physics, let's just ask NASA and see what they can do. So look at the space station here at lower right, down in that chamber where that arrow is originating there. There's a place where astronauts live that has equipment racks in the edge, and that's a exercise bicycle, perhaps not a fortuitously placed exercise bicycle. But if you zoom in there, there's a little sticker there that says Cold Atom Lab, and Cold Atom Lab plainly labeled on the edge. And that is a BEC machine in an equipment rack on the space station that is operating since 2018 or so mid 2018, and is presumably making condensates today. In fact, I very much hope it's making condensates today, because I think today is a day-to-day for my group. So it's a BEC machine in extended orbital microgravity. It's been up there for more than a couple of years now. And I try to explain this to people kind of outside the field, I guess, when I'm talking about this. It's not like quite like the Hubble Space Telescope, because obviously we're not looking at stars, but it's really trying to behave like a multi-user remote facility for study of a physical system. So it's a subscribable, I guess, we applied for time on this many years ago, and my group are now a user of this facility. And this is pretty foreign to the AMO, or especially the cold atom world. We tend to build bespoke apparatus for our own labs to measure things that we're interested in. So the apparatuses get optimized for the sort of specific needs of what we're envisioning. And this was kind of a radically different way of doing cold atom physics. It was a somewhat general purpose machine that was put out there, and proposals were sought to use a machine of generally, a fairly well specified set of capabilities. So I think that was tricky, because I never learned in grad school or postdoc how to deal with a user facility. Whereas I have peers in the kind of X-ray world or in the particle world who this is just how they think about how experiments work. Thinking about what a facility like that could actually offer Earth experimenters as a user facility. So in the absence of gravity, you can get to very, very weak traps and very, very low temperatures. And I think that's a goal of some of the other PIs who are using this machine. It's not my specific thing that I'm interested for the work we're doing, but it means you can get down to few hertz traps in the jargon, get down into the picokelvin scale temperatures, and actually have the atoms not fall and just sort of sit and hover in the middle of the vacuum chamber. So you can get very long time of flight expansion, free interrogation time, and the other PIs who are focused on doing atom interferometry with Cal are very excited about that. My particular excitement for this apparatus is that being in free fall eliminates this tilt. Any trap, which on Earth would be tilted at 100 nanokelvin per micron if you're using rubidium, which we are in this case, you don't have to deal with in orbit. And so any physical idea you have for doing experiments that is hampered by that tilt, that you can't cancel out with say, magnetic levitation, is now accessible in a BEC machine. Somewhat maybe sociology of science aspect, it actually adds sort of a user facility data approach to our field, which we haven't had before, which I think broadens the opportunities for researchers to study these facilities, especially if they're coming from institutions that maybe don't have access to their own BEC machines. And like most space-oriented hardware, there's upgrades that come along the way. And you can see a picture of an astronaut at the right installing the recent upgrade last year that was installed. So the folks at JPL did a just fantastic job building this and having it installed and having it work. It was a nice, lovely cover of nature just a little bit ago. It's all rack mount. It's inside the space station. It's not operated by astronauts. It's operated remotely. So the astronauts serve to install it and do upgrades, but they're generally out of the loop. You know, they're not tweaking mirrors or adjusting fibers or anything like that.
I'd like to note that color image in the nature cover comes from a image made by David Fader back in the early days of rotating BEC. Was drawn up by the NIST Public Affairs Department.
Oh, cool. Well, it's appropriately ethereal. So the work of my group in this collaboration has been trying to use this environment to make a bubble geometry BEC, or look at ultracold systems in this shell geometry. So how can we actually do this? I want to spend some time talking about the physical tricks that we want to use to actually accomplish this. This all got written up in this paper last year that summarized kind of 3 or 4 years of modeling from my group. And there's 4 or 5 undergrads there actually who've all done pretty bang up work helping with the modeling of this system over the years. But the central idea here is kind of an old friend to all cold atom physicists, is using RF coupling of Zeeman split spin states to basically turn on RF coupling in a trapped system and see what happens and see what we can do. So we don't have a 2-level system in reality, but it's great for illustrating things. So if we imagine a trapped spin system, so we have spin up, spin down, we have a trapping potential and an anti-trapping potential, and we couple them with radio frequency. So I turn on coupling field, some strength omega, and it's resonant at a particular point in space. So one way to think about this is actually by analogy, or sort of formally addressed potential, or sometimes it gets in the jargon, get referred to as the adiabatic potentials associated with this system. When I'm explaining it to students, I really just think of these as effective potentials, because if you're an atom strolling around in here, this is what you actually see. So the lower one here in red here is familiar to anyone who's ever done RF knife evaporative cooling, is where you turn on some RF and you selectively remove high energy states, high energy atoms from a trap. The upper potential is useful for new trap structures. So if we ramp up radio frequency from below, we can enter this blue potential here. Now, this is a 1D slice that I've shown here. So this is an effective way of making, say, a double well, and people have done this a lot on atom chips. The intuition that I like here is that this is a spatially dependent superposition of the bare basis. So depending where you are in space here, you're going to be in a different superposition of the bare states up and down. If you're far from resonance, or if you're far from this notch where the shell would live or a double well would live, you're either in up or down. But if you're sitting in there, you're actually in a superposition there. One of my students, I think last year, when I was explaining adiabatic rapid passage, had the sort of insight that a address state like this, or address potential, is a RF rapid passage whose completeness depends where you are. And that's a strained way of explaining, but it worked for that student, so I tend to stick with it sometimes. This all assumes that the coupling omega is strong enough that this is actually a faithful description of what's going on. If you don't have strong enough RF here, you don't create these potentials, and the atoms just leak down and keep sloshing around in the original trap. If we actually want to model this and understand it realistically, we have to use 5 states, not 2, because these experiments run in the F equals 2 ground state of rubidium-87, so 5-level system. And it ends up being fairly straightforward to just do a rotating frame transformation, do a rotating wave approximation, and you get a 5-state Hamiltonian that you can diagonalize to figure out what these potentials are. And the details of all this are in that modeling paper I referred to a little bit ago. The nice thing about this is the theory for this and these calculations are really accessible to, when I have undergrads who've come in and they've taken a year of quantum and they're raring to go, I can set the modeling code or let them loose on it, and they actually make fairly intuitive leaps with it fairly rapidly.
Nathan?
Yeah.
So why did you choose F equals 2 as opposed to F equals 1?
So the user facility chose that for us. But they choose it because the magnetic moment's stronger and they can make atom chip BECs faster. I think transferring to F equals 1 before doing these shell experiments, I think was going to be prohibitively hard for us to do. It's the sort of thing that you would have the freedom to do in a terrestrial lab, but actually ended up being kind of confusing with the remote facility. Does that make sense?
Sure. No, I was just wondering whether there was some other reason to say separate the you got better separation of the -2 and the +2 than you do for the -1 and the +1, and whether that was important. But that really wasn't part of your thinking.
It wasn't. And actually, if I had my druthers, if I was sort of doing this on my own, I think I would have started with the F equals 1 just for better simplicity.
Right.
So if you take these pictures, like that double well potential there, and you mentally rotate it into 3D, we can think of this as a shell potential or a bubble where the atoms want to live at the bottom of at a particular point in radius. And in practice, it'll be ellipsoidal. What's nice about this is that you can tailor the radius of that notch, and you can tailor the sharpness of that notch with your coupling strength and with your detuning from resonance. So we can dynamically inflate these structures, we can dynamically soften them, things like that. Fairly straightforwardly with the RF control that you presumably have on these machines. Looking at more realistic potentials on the right here, the atom chip presents a couple difficulties, namely in that there's a significant anharmonic nature to the atom chip potential. So you see they're plotted versus distance from a chip here. And the one we're going to be initially starting off is in yellow. So it's a very steep potential as you approach the chip, which is toward the left, and then it softens out to the right. So that means that anytime you do address potential like this, it's really not going to be as symmetric as you would like if you're doing this with a less anharmonic trap. So if you look at the address potentials we can make with this on the right, you can see one side of the bubble. By the way, is my mouse arrow visible to people?
Yes, it's a bit small, but it's definitely visible.
All right, so you can see the notch of that bubble slice potential there is actually tighter than the one on the right, and that'll have some inhomogeneity consequences for us. So again, if I had had my druthers, I might have been using F equals 1, I might have been using a sort of Yaffe-Pritchard macroscopic coil type harmonic trap, but it doesn't really matter because this actually is sufficient to do a lot of the things we're needing to do. So given that this technique has been known for a while, what's the point of microgravity? Why do we actually need it? And it turns out this gravitational tilt for rubidium, so in natural for me units, about 100 nanokelvin per micron. Depending on the radius of the shell, the BEC or the cold atom system won't be a shell, but it'll be a bowl. And this was first seen in 2006 in Brian DeMarco's group, and actually a little before in Helene Perrin's group in France. We make a shell starting with a magnetically trapped system, and you just see it work, but everything sags to the bottom. I put in the dashed lines to guide the eye there about where the sort of ellipse of where the atoms would lie in the absence of gravity. Chris Foote's group in Oxford has been doing stuff with this, with nested shells, so you can get almost nested contact lenses of atoms. on the left there. And the von Klitzen group in Crete has also been looking a lot at these systems. So it's pretty clear that the technique is viable for making shell structures, except that on Earth they're completely sag to the bottom due to the strength of gravity. All right, so if we actually want to exploit microgravity and do this aboard the space station, what do we have to do? So I guess step 0, we have to have a space station with a BEC machine. So thank you, NASA and JPL for that. But then we have to make a BEC and get to our preferred starting geometry. So atom chips, depending on how familiar people are with them, don't actually make a particularly round or spherical condensates to start off with. They tend to start off very pencil-like, very tightly trapped condensates, which are not going to be useful for these studies. So a lot of the hard work of actually doing experiments with this is actually getting the condensate away from what the user facility gives us, namely about a very pencil-like trap with aspect ratio of about 5, sometimes more. That's very close to the chip, and expanding and pushing it away from the chip here. And the conceit of this slide, which is a little belabored, I think, now that I look at it, is that we've got a space on the Earth at the bottom here. I've got an abstraction of the ISS and its environment here, and then the atom chip surface, and then inside the atom chip is up here is the condensate. And those gold guys there represent the atom chip traces. So if we want to do the experiments involving shells, we first have to control the experiment, chip currents, bias fields, to get this condensate away. But this involves physically moving an ultracold cloud, and that can be a pain because it's difficult to be adiabatic. You don't want it to be moving and sloshing and or even have other collective modes excited by that movement. So we spent a lot of time trying to figure out if we can actually move it and have it be still to do further experiments. Turns out we are generally able to do this. So we can create ramps guided by the literature, guided by just some sort of intuition about the mechanical properties of condensates, and vary the length of time of such a ramp. So maybe starting off on the right graph here, if we do an expansion ramp over, say, 120 milliseconds or so, we end up with sloshing amplitude more than 100 microns peak to peak, back and forth. So really terrible sloshing if we do that. But if we slow down and we move this condensate away from the chip a little slower, we can go actually get this down to the kind of submicron level. The analogy here that I like is, is carrying a big bowl of Jello from one side of the room to the other and having it be motionless at the end. You don't want to run with it at first, but you actually want to do it, not taking all day. So as long as you start off slow, then you can move for a while and then slowly back down. You can get to where you're going. I think there's a cottage industry of shortcuts to adiabaticity of people who do this with kind of tailored kicks and more clever ways to do it. We really just did this by taking a reasonable expansion waveform and doing it slower and slower. So if you look at the lower right graph on the left, if we do this over 500 milliseconds, the residual motion of this condensate after time of flight is down to a few pixels there, which actually is sort of 5-10 microns. But if we extrapolate back to what was in trap, it's below a micron. There's a little bit of heating associated with this process, but it's enough to get us somewhere for at least the first science run.
Nathan?
Yeah.
Looking at the time records of the things when it was sloshing a fair amount, and the dotted lines that you've superimposed, it sort of suggests a sinusoidal motion. But as you mentioned, the trap is anharmonic, not just overall, but it's also particularly anharmonic in the dressed. And so if the cloud had very much extent, you would expect some dephasing because of that anharmonicity. But the fact is, looking at the pictures, doesn't seem like there is much. So what's the deal?
So I think the short answer is that for the largest amplitude there, the 125, I don't think that actually lasted too long. I think it did start to get messy after that. But these are also with some fairly cold clouds as well.
So it's mainly because the cloud is really, really cold.
Yeah, but I mean, I would expect that you would actually see some dephase, or actually, if it was really hot or big, you wouldn't see necessarily a great fit here, depending on the size of the cloud. This is one of these things where if this was a terrestrial experiment, we would have had libraries of this from 0 to 300 milliseconds for 10 different expansion times. And this is where the bandwidth of data acquisition kind of comes into play. So each of those, I don't know, this roughly represents a couple days worth of work where you're only getting maybe a day or two a week over, and that's your data week. And then next month you get another data week. So we've had to be pretty careful in terms of extracting just the information we want and not much more for things like this. Does that make sense?
Sure, but I was just wondering, the limitation on the bandwidth, this is because other people are using the CAL for other experiments, for example. Is that
That's
why?
correct. The other PI user groups, so like Cass Sackett of Virginia has experiments he wants to run. Nick Bigelow and his collaboration has experiments he wants to run. The Cal people want to get potassium going. There's sort of maintenance runs that people are running, things like that.
Yeah.
And it's
the fact that you can run 24/7 doesn't quite make up for that.
Yeah, and actually the apparatus is it's not run 24/7. It's run about 8 hours a day.
Oh, and why is that?
That's a good question. I think there's a multitude of factors that fall into that. Some of them bureaucratic, some of them conservatism with the health of the machine. And some of it are, just sheer, I think, always wanting to have somebody keeping an eye on the machine. Honestly, I think that's a little bit above my pay grade.
Okay.
But it's there's a successor machine that's being planned, 4 or 5 years down the road to, run partially by the Germans, partially by NASA, called BCAL. And that was a central concern in the development of that. It was like, can we get more time on this machine during the day?
But it doesn't really require the astronauts to do anything, right?
No, the astronauts are all out of the loop.
Right. Thanks.
So practically how we actually do this with RF, it's an RF ramp. So we turn on RF power far from resonance, and then ramp the RF frequency up and up and up, and that actually deforms this potential and inflates to a given radius. And to figure out what actually it looked like, we can then turn off the RF, turn off the chip, and take a picture with standard absorption imaging practices. Realistically, this actually gets pretty messy because you need to take into account the graining of your RF ramp and have it not take too large steps. It helps if it's phase coherent. It helps if you can start far enough from resonance that you're truly adiabatic. A lot of these specific issues were worked out in the 2000s by the French group. Hélène Perrin really kind of figured out what aspects of the RF technology needed to be focused on to make this work, right? So we had some good guidance going into planning these experiments to start off with. All right, so this is, I guess, the first picture of data from the space station that I'll be showing you. So these are just proof that we actually have things that are condensates. So to orient you folks, there's an atom chip machine that roughly looks like that Cold Quanta machine at the right. Cold Quanta is actually the contractor that built the BEC machine that's at the heart of Cal. So there's an atom chip, and normally on Earth, the chip is at the top of that apparatus, and if you turned off your trap, it would fall down. So in these pictures at the left here, the chip is at the top, and if we make what we think is a BEC, but we haven't released it in a time of flight, or just 2 milliseconds of time of flight, it's at left. If we let it fall for 22 milliseconds, well, it doesn't fall. It stays in the same place. And that wasn't unexpected. We know we're in free fall, but it's great to see a cold cloud not move at all when you release it from its trap. Those of you who've seen a lot of condensates will probably immediately note that these are small, and actually not super high condensate fraction. So the one I'm showing you here on the right might be 20,000, 30,000 atoms, maybe 30, 40, 50% condensate fraction. Those numbers are typical. They have gotten, there have been better days and worse days with this data, but they're characteristic of the kind of typical data or typical starting user facility parameters we have here. This is after this expansion into the weaker trap. So the cloud here is probably a little below 100 nanokelvin, so maybe 80 or 90 nanokelvin with a critical temperature of 100 to give you that 30% or so condensed fraction. These imaging processes are destructive. So every time you take a picture, you've got to restart the process and make another one. The beam is parallel to the chip surface, so coming in horizontally on your screen for purposes of these cartoons here. And a kind of a good typical day would be about 1 condensate a minute and running about maybe 100 shots a day. So definitely a change in culture for, kind of a terrestrial lab where you might start your condensate machine in the morning, let it run all day. And even if you're just thinking about physics and not doing anything specific, you might take 1,000 shots in a day or more. So given that we have the ability to make small but reasonable condensates, let's try this process to inflate them and see what that looks like. And again, we're going to try to inflate to what I guess have a cartoon bubble there, probe beam coming in from one side and taking a picture on the other. All right, so to orient you with these pictures here, at upper left here is our bare condensate. And there's a dressing endpoint that I'm going to have in terms of a frequency shift, but it really is, you should think of it as a radius of a shell in that potential. So as we move to the right, getting a little bit bigger, still just looks like a blurred out blob, and we're under the limits of imaging resolution at this point. So it could very well be a shell structure under there, but it's blurred out for us right now. But as we go bigger and bigger and bigger, and there should be a scale on here, I think it's 400 microns, you end up with structures. And I think when we first saw these, we were just like, what is that? And I think one of the staff scientists at JPL said it looked like a Klingon or Romulan warbird, which I guess if you stare at it enough, it's menacing like that. So if we plug in what our kind of modeling expectations here are, is I'm going to see that dashed line around there representing a shell-like structure with the center being a green dot there. So the first thing you notice here is that everything seems biased toward one side, the lower half of your screen, which on one hand is, well, if this was gravity, you would see sag in that direction, but it would be much, much, much stronger. Second thing you see here is some non-uniformity around the edge. There's some non-uniformity around the surface. Looking at the time, I'm going to move a little bit faster to make sure I can show you guys some cooler things here. So anytime you see something with a cold cloud that doesn't make sense, it's sometimes helpful to just go with a hot cloud and see if it looks any more intuitive. So we can actually back off the ultracold limit of our initial sample and put in thermal atoms. And you see something maybe a little bit more coherent here, where this looks like a half of an arc of a shell structure, and you start seeing the top of it begin to fill in there. So the way we're interpreting this right now, and the way you should think of this, is that there's some residual inhomogeneity in the system that's causing a bias toward one side of these shell structures. It's complicated by the fact that we're looking at column density. So we've got an ellipsoidal shell that's partially filled that we're looking at a column density of, which distorts our picture of. So, oh yeah, there's a scale. So there's a 100 micron bar there. If you tried doing this on Earth, so the gravitational length scale, so KT over mg, is about a micron, maybe to a few microns for purposes of these pictures. So we're clearly doing things in these pictures that aren't possible terrestrially. So how can we actually interpret these? So we have a model that has been paid off so far in terms of predicting trap frequencies. So if we lay out everything we know and we feed it into just a dressed atom calculation starting with Biot-Savart, and we take into account some known uniformities, we can actually get some modeled column densities that start to look like what we've been seeing. So looking at the right, there's some choices about blurring and imaging optics that we've made. So comparing the cold data there at the right and the hot data at the bottom with its partner on the right, you start seeing some qualitative agreement with what we're seeing in the apparatus. If we actually take slices in the model rather than a column density, it's actually more reassuring to actually see slices through a shell. The fact that it's an ellipsoidal column density tends to distort things. And I think by request from a previous talk, if you actually apply 10 milli-G or so to these apparatus, to these models, you just get complete pinning to one side of the shell structures. And this is just 1% of G. So that's kind of an exciting check that whatever we're doing here is totally impossible terrestrially. So why not go bigger? Let's see how big we can make these just to understand the limits. So we can go up to kind of millimeter or even 2 millimeter scale there. So you can see what's starting to happen here is the cloud gets bigger and bigger just because the atoms are spread over larger and larger shells. You run into some signal to noise issues with the larger shells. But it's pretty exciting to see that these arcs, and they think of these as now bowls of atoms with maybe faint coverage on the upper half of the bowl, still are visible and still are, we can work with them at multiple millimeter length scales.
Sorry, can I ask a quick question?
Yeah.
So that hard edge on the right, is that the atom chip itself? And is that cloud
exactly.
actually starting to evaporate on the chip?
We're about, so if we actually went further, that would be a problem. I think if you looked at the shape of the equipotentials here, the curvature is not as strong on the right side. So I think we're just probably starting to abut on the right side. There's that would be a really neat experiment to try to go bigger and actually see then the atoms disappear when you hit some critical size. And if you do some sequential takes and you make a movie of it, you can kind of see this inflation work like that. The residual cloud you see in the middle is actually on the viewer's side, or it's on the shell, but on the direction to and from the viewer. They're not actually at the center of the ellipsoid.
Are we looking at thermal clouds now in those pictures?
They started off thermal. So I'm going to try to get to a couple data graphs in a second that'll clarify that a little bit more. But it turns out if you try to start with a BEC and you get that big, the signal to noise ratio really starts to kill you. So this was more of an illustrative, what can we do with hot atoms starting off to see how big they can go. All right, so I'm going to zip through the various inhomogeneities that we're worried about, but it turns out the main culprit is the fact that the RF coupling is inhomogeneous. There's a single loop of wire driving this RF, and the condensator of the shell is located exactly at the most non-uniform part of that RF. So from one side of the shell to the other, the RF power or the Rabi frequency changes by about 0.5% to 1%, which really affects shows up as a tilt in these dress potentials. And that could be, we have an upgraded machine now that has a bigger antenna to try to work with that. All right, so there's some interesting thermodynamics, and I maybe want to finish with the thermodynamics aspect here. To understand what's going on with this, as we inflate, think of an initial cloud, whether it's condensed or not, as having some initial entropy. And as we inflate, temperature is going to drop. Well, temperature is going to change. Critical temperature is going to change. Phase space density is going to change, and number is going to change if there's a little bit of loss process. But the condensate fraction will also change as well. So as we deform into a shell, you should think of the shell squeezing, so the atoms are getting compressed into a tighter surface, but they're also being spread out around the whole surface. So the net effect is actually going to be adiabatic cooling. So this has actually been known for a long time, but you can have situations where you lose or gain phase space density at constant entropy. And this is what we're doing here. We're nominally adiabatic, but unfortunately, phase space density actually will drop at constant entropy for us. A gain of phase space density at constant entropy is actually a well-known tool. This sort of there's actually a Ian and Trey paper from 10 years ago there, but this trick has also been known in other contexts as well. For us, unfortunately, what it means is that and I want to look at the graph on the right here. As you inflate a cloud, temperature is going to drop, but TC will actually drop faster. So this is a calculation, but if we start off at around maybe 90% of a critical temperature with a condensate, and we start inflating, TC in blue drops faster than the temperatures. And remember, we're still adiabatic here, so you actually will have the gas being driven normal in this expansion if you're not careful. And that's actually it's probably there's going to be non-adiabatic effects as well, but you're already fighting hard against this effect, which actually is pretty. I didn't know this going to this. This was going to be an effect. Another way to understand this is that the entropy at TC changes as a function of this shape of this potential, and 3.6 entropy units per particle at TC is well known for harmonically trapped BECs. This drops like a rock and then crawls back up. So maybe at really large radii, we might see it become a condensate again, but adiabaticity would probably be an issue. So maybe finish up with some actual data here. So starting with 4 different temperatures and inflating them, we want to track and see what happens to those temperatures. So if we start very, very thermal at left, start with maybe 600 nanokelvin in this cloud, so maybe 6 times TC, and we inflate it, and those cartoons at the bottom there should guide you as to what the cloud, the potential might look like. You see temperature drops like a rock as it immediately goes into a shell-like configuration, and then goes some more gradual, slow cooling like that. Our model of this and looking at the thermodynamics of these shells matches up with this quite nicely, but the colder we try to get, the worse things get. So switching over to the far right, if we start off with something that's maybe partially condensed, maybe 90% condensate fraction, or sorry, 50% condensate fraction, the T over TC of 0.9. As we try to cool, it should be dropping down to the 10 or 20 nanokelvin range, but what we actually see is 50 or 60 with some pretty big error bars. So what's going on here? There could be mechanical adiabaticity issues here. Actually, this inflation has, I think, some pretty delicate parts, especially as you go from a well to a hump in the middle of the potential. But we haven't made an extensive study of this yet. And I think that's a pretty clear thing to try next. It's also possible that the thermometry for these large shells is not working right. And I think you can look at the raw data and where we're trying to extract temperatures from. So we start with a shell-like structure at left, and it gets bigger and bigger, and you try to extract a temperature from this. And that can be a little tricky, as any of you folks in the audience who have done thermometry of clouds can know. And likely both of these effects are playing a role. We don't really have a great understanding of the imaging specifics, or I think is a current project as well. All right, so where are we at here with this? So on one hand, great news, we've seen structures distinctly unlike terrestrial equivalents. We understand where it's coming from. We understand where these residual inhomogeneities. But what we don't really have a great handle on is what's happening to these initial condensates when we try to inflate them. They stop being condensates. Is that because we're not being careful? Is that partially because of some of these thermodynamic effects? Is it just actually bad thermometry? Is it something we can improve through better data analysis? That's all kind of what is on our plate right now in the second science run. And bigger ideas, with this second and hopefully maybe a third science run, was actually add some complications to these shells. There's some ideas to use microwave dressing to cancel out these inhomogeneities, to have use the microwave loop to do to dress the dress levels and in such a way that the inhomogeneities cancel out. That's a neat idea I've been trying to work out with Barry Garraway and his student. And again, focusing on the sort of bigger picture physics goals, trying to actually see a dimensionality crossover and see if anything interesting shows up in the experiment when we do that. Most of the theorists who contacted me to talk about this stuff and that we're in conversation with want to talk about vortices and how they behave in curved manifolds and things like hedgehog combing theorems and things like that, and what it means to have vortices and anti-vortices in closed 2D geometries. But the nice thing is that it appears to be kind of a nice supportive theory community associated with this line of investigation starting. And this is just from 2 days ago, kind of with the new apparatus, a hint of the kind of neater new things we're seeing, which are looking a lot more uniform and actually more tantalizingly circular or shell-like. But I probably shouldn't spend too much time on that. All right, so there's a lot of people I want to kind of give shout outs to here, but I've had just fantastic people in my group over the last few years, some great postdocs and current postdoc Joe Murphy, and a kind of succession of just awesome undergrads. My theory collaborators are Courtney and Smitha, and Smitha's group at Illinois right now. Brendan Rhino is doing really awesome stat mech and thermo calculations for us. None of this is possible without actually the folks at JPL. Dave Aveline is my co-I there, and he's also the science module lead there. And along the way, we actually spent a lot of time talking about with the successor experiment, BCAL, hopefully launching in 24 or 25 to the space station, which will replace CAL, and we would hope to be involved in that to some degree then. And I think just about over time, I would love to stop and take more questions about this stuff.
All right, so the floor is open for questions.
It's Charles. I guess, you know, it really, maybe no one knows the answers. What are the realistic prospects for a replacement of the existing space station? Is there a new one under construction?
Not that I know of. I think the end date of the current space station, I don't know. I don't know if there's any NASA people, you know, who are on this call, but I go to a lot of NASA talks, and I think people, you know, they do mention that the space station isn't going to be around forever, but when it stops is not, that's opaque to me. And I don't know what is necessarily going to replace it. I think the better case that can be made for not just physics, but science in general aboard the space station that is maybe relies on the space station rather than a free flyer is going to impact that decision a lot. So I don't know, maybe next generation upgrades to this will actually involve the astronauts more, and we want to find ways to involve the astronauts more if we want to have a space station doing this kind of stuff. Yeah, I would actually, if you've heard anything, you should tell me, because I think this has been a fantastic user facility so far, and I'd love to see it continue as long as possible.
Nathan, this is Bill. About the issue of the fact that the condensate disappears, heats up, whatever, as you expand. Even though I don't have anything to offer, it's not all that surprising. I mean, people have seen that when you try to move condensates around, they're pretty fragile, and it's easy to heat them up. And people often will try to do most of their motion with the thermal cloud, maybe just above condensation, and then evaporate once they've got the condensate where they want it. But in your case, of course, your density is a lot lower after you've done your manipulation. So is that the main reason why that wouldn't be a good procedure for you, that the evaporative cooling would just go really, really slowly if you tried to go to a condensate after you've expanded?
It's not so complicated as that. I think the initial issue was that even though evaporative cooling in address potential, actually Helene Perrin's group had done that, and I think if they're careful, it's possible, but the density is a concern. The trouble is we didn't actually have access to a second RF signal. But that turns out that we've actually found a kind of a tricky way around that. It turns out that second antenna, which was just for microwaves, that you can run that amplifier actually will go down to RF. They never bothered mentioning it because it's going to be way lower power, but it actually might be sufficient for what we're doing. So trying to do a second RF tone, either just for RF spectroscopy of the dress state, or to try to actually do evaporation in these, that's something I would hope to have done by the second run. But it's not going to be great evaporation just because of the density and the fact that you just don't have a ton of atoms here.
Yeah. Okay.
You actually do get squeezed fairly tightly. The bigger these shells get, the tighter the bubble frequency gets. So you could actually end up, those millimeter scale ones might be a couple kilohertz tight along
Yeah.
with the perpendicular direction. The other thing we could try to do is some kind of microwave evaporation. There's a microwave coil as well.
So Nathan, this is Trey. I had a couple of questions. The first thing is, I'm given my long experience with working in a lab, things always go wrong, and you have to like tweak a knob, as you say, that this thing doesn't require. I'm curious as to how working with a sort of fixed apparatus goes, and how you know, like, is there you talked about the bandwidth of the amplifier being able to go down to low frequencies, but that means you need a VCO or a synthesizer that goes down that low as well too, and it's all sort of in place. How different is it working, you know, in that kind of environment? And do you have to like interface with the engineers to know like what exactly exists and is capable?
Well, I think it takes a lot of patience for sure, because you can't just go in and toss in a quick indicator. Hey, here's another loop. You know, here's another antenna. Let's just try this today and see if it works. Generally, what happens is that we float an idea to the JPL people, and they have an internal, you know, new idea evaluation process, which basically prioritizes not damaging the machine. So they have to test it out on there's a ground test bed machine. So any kind of tinkering type idea like that tends to have a multi-week, you know, make sure it doesn't hurt the test bed on the ground, and then you can try it out. The day-to-day tweaking, though, that you're also asking about, basically what that means is that some days I get access, we get our data runs starting at like, you know, 2 or 3 Eastern. Other times we don't get it until 6 or 7 Eastern. I think it depends how long the operators of the machine take to get it into making good condensates. And some days, like, you know, it turns on and it just works. Other days they have to massage it for a few hours to get it to work, just like any terrestrial machine. And it's the sort of things that you would probably imagine, like some laser power, laser lock issues. But other times it's driven by communications with the space station. Sometimes it's driven by hardware hangs that require more aggressive reboots than you would necessarily have on Earth. You know, a lot of it is driven by conservatism, that whatever you do, you can't screw up the machine in such a way that you can't fix it. And that means a lot of the tricks you would try in a terrestrial lab, which are okay because you're right there to do damage control, you can't do with a remote machine. So that can be, you know, that's hard at times for sure. But I think actually, when I see new pictures show up in my feed, and I, you know, from the space station, it takes away the sting.
Okay. So the other question I had was, in the images, quite frequently there are two kind of high density points at the edge of the shell that seem higher than just the column density would from the model. And I'm just curious, is that some inhomogeneity, or like what causes that at the edge of the smile?
So there's two things going on here. One is there definitely is a inhomogeneity biasing to the top and bottom of your screen here, as well as to the left. And that basically comes from, there's a wandering of the local bias field away from being perpendicular with the RF. So if the RF is up and down in your screen, and the bias, most of the areas in the trap is left and right, as you move around in the trap, it deviates a little bit. So you get a little reduction in the actual coupling strength there. And that shows up as a sort of lower potential at top and bottom here, but it's amplified by column density. So if you look at lower right here, if I look at the model and I don't really blur it at all, that effect, okay, it looks a little darker left and right, but it's not quite as pronounced. But the more we blur this, the more we take into account finite resolution, it actually tends to visually accentuate it. So you kind of say, wow, there are these golf balls at the end of the smile. that if you actually had just a true high resolution slice, it wouldn't be as dramatic.
Mhm.
Part of the problem here is we've got a multi-hundred micron extended object that is larger than, say, a depth of field, but does that actually necessarily matter? Imaging is a little complicated when you get objects that size. And I'm being a little waffly there because there's actually kind of some hearty arguments about the best way to understand the imaging and for objects this large in the collaboration right now. I don't think there's arguments, but other people do.
Nathan, this is Bill again. You sort of teased us with talk about vortices and the special situations, and I've talked with you about this before, and we've talked with Vanderlei Bagnato and Sandy Federer about this, and so one of the things that came out of those discussions was that if you had a spherical shell, that there's no such thing as a single vortex. It always has to be a pair of vortices, and I would presume that that's going to be true for any topological distortion of the sphere. But I was wondering whether there's anything more cool that you could tell us about, whether things have changed in the thinking that you've done about that since then.
So I think that's basically a good summary. I think looking for that is complicated though, because say you do this, an aggressive expansion, are you going to see vortices way more than that nucleate? Like getting down to just showing that there's a minimum of 2 is going to be hard. I think I've also gotten curious about to what extent curvature plays a role. So the vortices, I think, will experience an effective potential related to the curvature, where I think they'll want a pool where there's most curvature, I believe. So trying to, that way of thinking, maybe an ellipsoidal one might actually be more interesting to look at and show more interesting behavior than a purely spherical one. But this basic idea of looking for a bare minimum, sort of always needing to have some minimum level of singularities, that really is that basic idea there. I haven't done a ton of elaboration beyond that. There are people, a long time ago who looked at I think superfluid helium on little nanopillars, looking for sort of curvature effects there. And I don't know if there's any insight to be had from that, but I've seen that mentioned a few times.
Do you have any way of stirring the shell condensate?
Not in the obvious way you're thinking of, poking it with a beam and moving it. Hopefully BCAL, the successor experiment, will have a stirring rod like that. So any way we would have to generate vortices would have to come from some kind of excitation of the trap, or just, I don't know, maybe just start off with a thermal cloud in the shell potential and evaporate and just look to see Kibble-Zurich kind of vortices showing up and seeing what happens with them.
Yeah, I mean, that's obviously something you could do, but it's a little less satisfying than doing a deterministic stirring. Well, you mentioned distorting the trap. Can you distort the trap in such a way that you effectively rotate it and end up with vortices appearing in the way that might be analogous to the way you do it in an asymmetric normal trap?
So think of doing some kind of time orbiting potential with the bias fields to try to add make it look like it was rotating.
Well, it wasn't. I mean, a time ordering potential might be a way to do it, but just changing the currents in a magnetostatic trap might allow you to rotate it.
Yeah, so I can imagine jumping from one trap configuration to another that had an angular rotation associated with it, and trying to give it an angular kick without distorting the trap shape too much.
You would probably need more wires, but
well, we have there's independent 3-axis coils. We mostly so we can apply gradients. Although the gradients don't help that much.
Yeah.
But there's reasonable time-dependent control of these. maybe not in like a time orbiting way, but certainly in kicks back and forth. So you could try to give the cloud an angular kick and see what develops.
Yeah, that's not ridiculous actually. Giving it a kick. I was thinking more of giving it a rotation and reaching a critical rotation speed so that a vortex enters.
The other tool we have to play with are these atom interferometry beams. So we actually have access. We could do Bragg spectroscopy of it.
Yeah,
so
right.
There's counterpropagating Bragg beams.
Yeah, so if you had an LG beam and did Bragg on that, that could be. But they probably haven't built LG into the system, have they?
No, it's pretty bare bones Bragg. But I mean, they're seeing good atom interferometer signals so far. But so it's enough that we could try to do some kind of. I mean, one way that you could think of if we are mystified as to whether or not we have a condensate or not because of bad thermometry or the imaging is blurry, is we could try to figure out if we have a condensate or not by doing Bragg spectroscopy, right? Like, I think this is a pretty old trick.
Sure. Okay, thanks.